Okay, so thank you, the organizers from both the colleges. And I actually love to talk to the youngsters, particularly the college students, because I don't get much scope of talking with them. So it's a nice opportunity. Thank you for giving me that opportunity. I would have loved to talk to them in person, but given the present situation, I guess the webinar is not a very bad option. Okay, so since this is a national level conference, national level program, so I'll be talking in English, but if you have any questions, this is particularly for the students, if you have any questions, you are free to ask the questions in Bengali. আমি বাংলায় চেষ্টা করব তোমাদের উত্তর দিতে যদি তোমাদের বাংলায় কোনো প্রশ্ন থাকে সো ডোন্ট হেজিটেট ওকে দিস ইজ দ্য মিডিয়াম উই আর ইউজিং বিকজ দিস ইজ আ ন্যাশনাল লেভেল প্রোগ্রাম বাট যদি মনে হয় তোমাদের বাংলায় প্রশ্ন করলে তোমরা তোমাদের পক্ষে কমফোর্টেবল হয় তোমরা বাংলায় প্রশ্ন করতে পারো আমি বাংলায় উত্তর দেব কোনো অসুবিধা নেই সো ইজ ইট অলরাইট লাইক আই মিন Shatuki, is it অলরাইট লাইক Okay,
it's perfectly fine.
Okay, yeah. Fine. So, and I have been also requested to cover a part of your astronomy and astrophysics curriculum that is there in your BSc and MSc level. Now, since this is not possible to cover every bit of it, this is a 1 semester or 2 semester course, I guess. So I'll try to cover up, I will basically try to touch upon a few topics that will be a part of my discussions. Let me just give the names of a few. I've just copied from your astrophysics course and all these things. So I'll basically touch upon the Milky Way galaxy, rotation curve, then virial theorem, then little bit about dark matter, how we can get the hint of dark matter from rotation curve. Then I will talk about a little bit about the redshift and Feynman cosmology, then lambda CDM cosmology, Hubble's laws, little bit about dark energy, then about CMB anisotropy, then some experiments like OB, WMAP and all these things, and then about large-scale structures. So this is, so I'm just giving you the names because if you go through your syllabus, you can find that out, that these are there as part of your astronomy curriculum, both at UG and PG level, and they are mostly a part of cosmology. Cosmology, as you have already heard about from the first speaker, that this is a part of astrophysics course. Shall basically take glimpses of those topics in my own language, and I'll try to talk about this topic. The topic is Unveiling the Mysteries of Our Universe with Telescopes. So this is my plan, and I'll try to finish within 50 minutes. And this is a huge topic, so I'll try to cover up as much as possible. But I can stop anytime if the time is over. Okay, no problem. Okay, so with this small introduction, let me start with this. So the point I'm going to highlight on this, so this is basically the summary of my talk. I usually try to keep the summary of my talk at the very beginning. So this is the summary of my talk. The summary is a little bit philosophical. So the summary is that the purpose of doing science is not just to help you brew your morning coffee. So whatever we do in our day-to-day life, one purpose of doing science is, of course, to make our life much more easier, much more comfortable. But all I'll try to focus upon, or I'll try to convince you in the next 50 minutes or so, is that the purpose of doing science is much more bigger than that. Okay, so what is the purpose I'll try to talk about, and I hope that you'll get a glimpse of that. But so this is basically the final slide, that the purpose of doing science is not just to help in our day-to-day life, not just to make it easier, but to go beyond that. But the horizon is really much more big than that. So this is basically the bottom line of my talk that I usually try to give at the very beginning, so that in case you feel bored or you feel sleepy, you can go to sleep very well, and you can get up at the end of 50 minutes and say, well, I have learned whatever you have been talking about. Okay, so that's it. Okay, so let's start with this little bit more technical. So I'll try to develop my talk from our understanding of the subject, and I'll just assume that you have, of course, you have class 11, 12 kind of knowledge of science, of course, but on top of that, you have little bit knowledge about your BSc level physics. So based on that, I'll basically try to develop all these things, and mostly I'll basically develop my talk with some pictures and diagrams with little bit of plots at the most, but I'll try to avoid any mathematical equation, so this is the purpose, because the mathematical aspects are much more complicated of the subject, so I'll try to avoid that. Okay, so don't worry. We'll basically see some pictures, and we'll talk about those pictures. I hope that will be okay for, in particular, for the BSc level students. Okay. So this is the night sky with naked eye. All of us we see about this, and in order to see this night sky, we don't need any kind of knowledge of science. This is what you can see at the night. But if we want to probe little bit into details, because human civilization that is based on a question, the question is curiosity. So what is there beyond our sense of perception? What is there, and can we understand that? So in order to understand those things beyond our sense of perception, beyond our naked eye, what people did is this. They tried to go beyond our sense of perception. What they did is that they built up telescopes. You know the story, from around 400 years back, a guy called Galileo Galilei, he first developed a telescope, and using that telescope, he basically for the first time, I guess some background knowledge is coming. Okay, fine. So, for the first time, experimentally, he said that in our solar system, the sun is. I mean, if any microphone is on, please can I request that you need to put it off? I mean, is it okay? Okay, fine. So what he did is that for the first time, he proved using the telescopes, because physics is an experimental subject. So he proved that in our solar system, sun is at the center, and all the other planets, including our Mother Earth, they are basically rotating around the sun. So this is the first time he did, and this is the cartoon of that telescope. All of us know about that. This is the cartoon. Sorry, just a minute. So this is the cartoon, but during the last 400 years or so, the technology has advanced, science has advanced in all these things, and nowadays we have lots of highly sophisticated, highly precise, and much more developed telescopes, and we can broadly categorize those telescopes in two types. Don't worry, I'll talk about those telescopes in a bit details. Okay, but we can broadly categorize the telescopes based on the wavelength range they are probing. All of us know about wavelength. It can be optical. It can have wavelength. It can have the capacity to catch the waves of X-ray level. The wavelengths are much more lower, much more smaller than the optical range, or it can have a higher kind of range, which is radio wave. So based on that, based on the wavelengths, you can have three different kinds of telescopes. And also based on positions, you can have three different kinds of telescopes. Of course, it can be ground-based. It can be placed in underground. I'll give particular example of each one in a minute. Or it can be space-based, which we call artificial satellites. And all we need to do is, using those telescopes, all we need to do is to do this list. We need to collect the data, and then we need to analyze and interpret the data. And at the end of the day, we need to build the models using our understanding of physics, and we need to explain whatever data we're getting. So this is the purpose of doing astrophysics and cosmology. And basically, I'll try to brush upon some of the steps we have found out right now, which mostly focuses on the cosmological aspect, so to say. Okay, so here are particular examples. I'll talk about them in details later on. The ground-based telescopes, as we have already seen, the Galileo kind of telescope that has developed to a great extent. And nowadays, what we call is not a particular telescope, we call it an observatory. And this is how an observatory looks like. So this is an observatory. This is a huge kind of building, inside which you can get highly sophisticated kind of telescope or a combination of telescopes. They collect all the kinds of data that is available from outer space. And there are lots of highly sophisticated computers over there. The data comes and falls in the computer, that is accumulated inside the computer. And we basically collect the data, and we, as I said, that the three steps of collection of data, and then analyzing and interpretation of data. And at the end of the day, we need to build models based on our understanding of the subject. So this is ground-based, one example of that. The second one is space-based. I'm sure all of you have heard about this. This is called Hubble Space Telescope. This was basically, so this is the telescope, and this is our Mother Earth. So this is basically rotating around the Earth in a particular orbit, and this is giving us the data. And last year it was the 25th year of running of the Hubble Space Telescopes, and this is giving us huge amount of precise data. And from there we are basically getting to know about our outer space, about our universe as a whole, to a great extent. I will talk about that in a bit details. I'm just trying to motivate you about different kinds of telescopes. And if you zoom in, this is a zoomed in figure of Hubble Space Telescope. You can see a guy sitting over there. So just try to think about that. This is just 10% of the total telescope, so to say, and guy looks like that small over there. So just think about the size of the telescope and just think about the power of human intelligence. This huge amount of telescope have been thrown in the outer space and have been put in a particular kind of orbit and have been successfully installed there, and this is giving us huge amount of data for the last 25 years at a stretch. So herein lies the power of human excellence, that is human intelligence, that I'm going to focus on repeatedly in my talk, so to say. And the third one is underground. This is called South Pole Telescope. As the name goes, this telescope is there in the underground of the South Pole, and this looks like this. So I'm sure all of you are thinking about that. Look, come on, this is not that impressive. I mean, we cannot see anything. Why we cannot see anything, I'll come to that in the next 30 minutes or so. And once again, after 20-30 minutes or so, I'll come back to this telescope and I'll talk about this. And maybe I mean, till that point, please hold on. So this is called South Pole Telescope. So these are three particular examples, but as I'll show, there are lots of other telescopes, and I'll talk about them in a bit details during the rest of my lecture, so to say. So the point I'm going to highlight on, I broadly categorized them into three parts. One, the first one is called dark. I'll talk about the others later on. So what I mean by dark? Come on, I mean, as we said, in the using the telescopes, our purpose was to see the light. Okay, purpose was to see whatever we cannot see. But now I'm talking about dark. So what does that mean? Okay, and here I'll basically come to your curriculum, so to say, a part of your curriculum, and that is this. So this is our galaxy, Milky Way. Once again, we know from our popular science knowledge and all these things, from TV programs or from YouTube and all these things. So this is our galaxy. This is the Milky Way. And it is constituted of millions of stars and all these things. And our solar system, even if it appears to be a huge one, our solar system is nothing but a particular dot somewhere inside the Milky Way. Okay, so you can just think about the size of our own galaxy. So this is our galaxy, and each particular dot represents a particular star, and our sun is one such dot, nothing else. So this is our galaxy. This is called Milky Way, and we can even with naked eye, you can see the Milky Way if you go to Ladakh, or even from villages. If the sky is really clear at night, we can have a little bit glimpse of Milky Way. So this is our galaxy, and we are basically sitting somewhere inside the galaxy in our own solar system. So this is the Milky Way, but going beyond that thing a bit, I mean, if you look into this Milky Way in a bit scientific, from some scientific outlook, you should look into Milky Way like this. So this is another cross section on Milky Way. Let me just explain a little bit. This is, so it's not, so our usual perception is that any astrophysical object should look like it's a sphere. Like our Earth is a sphere, Sun is a sphere, Moon is a sphere, Jupiter, Mars, everybody is a sphere. But it's not the case everywhere. The galaxies are different kinds of galaxies are there. This particular kind of galaxy is called spiral galaxy. It doesn't look like a sphere. It looks like a disk. The center is has a spherical shape, and most of the stars and all these things are inside the center. But outside the center, it basically looks like a disk. It's a 2D surface, more or less, two-dimensional surface. And you can see lots of tails are there. It's not uniform. Okay, it's not like এটা থালার মতো দেখতে নয়, তাই তো? বাংলায় বললে, যারা বাংলা একটু কনফিউজড হচ্ছো, বাংলায় বললে এটা থালার মতো দেখতে নয়. So it's like একটা করে লেজ দেখতে পাচ্ছ তোমরা. So their tails, they are called tails of the galaxy. So inside this is called bulge, and outside you have this. Inside this is called galaxy core or bulge, and outside you have this disk or tails. So what they basically tell us is that these tails are basically made up of neutral hydrogen. All of us know about hydrogen, and we know about its excited states from our knowledge of atomic physics. So these tails, they are made up of mostly neutral hydrogen cloud. And this neutral hydrogen cloud, they look like this. This is a little bit colored. I'm not going into the color code and all these things, But this is what we see using our radio telescope. I'll talk about that in a bit details later on. But these neutral hydrogens inside our Milky Way or inside any spiral galaxy, they basically encode a huge amount of physical information that I am going to talk about. Let me just go into that in a bit details. Yes, so this one. We know that neutral hydrogen from our BSc level knowledge, we know that neutral hydrogen, and any hydrogen that is made up of a proton inside the nucleus, and there is one electron that is rotating around the proton in stable circular orbit. And we know about the spins of electrons. So electrons can have spin up and spin down. So you can have two different states when both the proton and electron they have same spin, or other state when proton has spin up and neutron has spin down, or vice versa. We know, I mean, one is called singlet state, the other one is called triplet state. This is, I'm sure you know about this thing from your atomic physics kind of knowledge. So now all I want to stress upon is that 80% of visible matter is made up of neutral hydrogen. So stars and galaxies and all these things, they are just 20% of visible matter. Most of the part is 80%. That is a huge amount of neutral hydrogen cloud that I have already shown to you. And neutral hydrogen from our atomic physics knowledge, we know that it has singlet state as well as triplet state. And also from our atomic physics knowledge, we know that there is little bit of energy difference between them. And it can flip the spin. The electron can flip the spin. So basically the state, it can basically jump from one state to the other state because of this energy difference. And we know the name. The name is called hyperfine transition or hyperfine splitting. I'm sure in your atomic physics course you have learned about that fine structure, hyperfine structure, and all these things. So this happens automatically in our outer space. This happens in any kind of spiral galaxy, including our own galaxy Milky Way. So because of slight amount of energy difference between them, whenever an electron jumps from one state to the other, this energy difference that is either being emitted or being radiated from outer space, from that neutral hydrogen, from huge amount of neutral hydrogen, and sitting inside our mother Earth, using our telescopes, using our brain, using our knowledge, using our technology, using our radio telescope, we can catch that thing. And you can measure, basically, it's a very, very little amount of mathematics even from our 11, 12 kind of knowledge. We know E equals H nu, so we can catch the wave, we can catch the wavelength. Using that thing, we can catch the frequency, and from there we can find out the wavelength. Typically, the frequency becomes 1420 megahertz, or you can find out, and if you know frequency, then you can find out the wavelength by dividing it by C by nu is your lambda. So the wavelength becomes 21 centimeters. So that is why this is called 21 centimeter cosmology. I guess I'm not going too fast. I mean, can I get a feedback from anyone? আমি কি খুব তাড়াতাড়ি বলছি? Should I slow down or what?
না, আপনি বলুন, ঠিক আছে, ভালো।
Okay, thank you very much. Thank you very much. Okay, so that is why the typical wavelength is 21 centimeters. So that is why this is called 21 centimeter cosmology. So this is all about information, but what is the inference from there? What is the physics after that? So this is I'm going to talk about right now. So what we do is that using these waves and all these things, we basically measure the rotational velocity of neutral hydrogen clouds. So you have spiral galaxies, everybody is rotating around the galaxy core, and we basically try to measure the rotational velocity, and then we draw this kind of plot. So along x-axis we basically plot the distance from the center of the spiral galaxy, and along y-axis we basically put the velocity, the rotational velocity of each neutral hydrogen atom, so to say. Okay, so this is what you can do using even residing inside our Earth using our telescopes. And if we do that, then even forget about general theory of relativity and all these things. From Newtonian mechanics, you can draw the conclusion. That is really funny. So if you use Newtonian mechanics, what is your expectation? You know Newton's law of gravity. What does it give you? mv square by r. So since this is stable circular orbit, there are two forces acting on them, and that are basically balancing each other. One is your centrifugal force, and the other one is gravitational pull. They are basically balancing each other. That is why this is rotating in a stable circular orbit. The stability is guaranteed. Okay. So if we balance them, that is mv square by r. If we equate that thing to gmm by r squared, this is simple pen and paper calculation. You can do it right now. So mv square by r equals gmm by r squared. Then if I want to ask you what is V as function of R given this thing. So this is what I have plotted. So all you can do is that inside the galaxy, what you do, even inside an earth, what you do, you basically write down the mass as the effective mass as 4/3 pi r cube rho, right? When rho is the density. So if you replace mass m by 4/3 pi r cube rho, you can find out V as function of R, and you can readily show is that so long as this is inside the galaxy, the velocity is proportional to R. V is proportional to R. So that is why this is, you can just see there are two plots. One is expected from luminous disk. This is what you get from theory. So it should, along with R, this should linearly basically evolve. So V should be proportional to R. But outside the galaxy, the total mass, the entire mass basically you need to take into account. So m is a constant over here, and then V is basically proportional to 1 by square root of R. This is simple calculation using Newtonian mechanics. You can do. So basically, till this is inside the galaxy, it should grow linearly, and after that, it should fall off as 1 by square root of R. And this is what I have written down. The plot that is expected from luminous disk. I'm sure everybody can read it. So this is what is expected from our understanding of the physics. But there is another plot you see that is observed. This is what you get from telescopes. The experiment, as I was talking about, this is what you get. And what you see is really, really surprising, that there is a huge amount of mismatch between the two. What you expect from your understanding of physics and what you get from experiments. So there is a huge mismatch. Now, how to explain that? First and foremost, you need to ask the question whether or not there is any problem with experiments. So we redo the experiment, and people have redone the experiment millions and millions of times, not only with our own Milky Way galaxy. You can find out in our universe, I'll come to that point, you can find out in our universe millions of spiral galaxies. And so far, people have found out millions of spiral galaxies. And for each spiral galaxy, this nature has been observed from experiment. So the conclusion is that there is no problem with the experiment. The problem is with your understanding of the subject, understanding of theory. And the only way by which you can match the experimental results, since physics is primarily an experimental subject, you will have to rely on the experiment at the end of the day. So you have to modify your understanding of the subject. And here lies the real surprise. The only way by which you can explain the experiment is by considering that outside the spiral galaxy, along with visible matter, there is huge amount of matter that we cannot see using our telescopes. Because if we have a huge amount of matter, that can give rise to the extra amount of acceleration so that you can explain the observed plot. Okay, if you have extra amount of matter, then it won't fall off, like as you see from the theoretical plot. Okay, it will still be rising. That is what you get from observation. And that gives you the first hint that whatever we see using our telescopes, even beyond that, there is some kind of thing that must be there, that is there. Just because it does not emit any kind of light, emit any kind of wave, we cannot see it. So this is the first hint, and here you can see that thing. I mean, inside you see the galaxy, the spiral galaxy, and outside the spiral galaxy, you can see a blue halo kind of thing. So this blue halo kind of thing is called dark matter halo, and this gives you, I mean, way back in 1930s, we got this kind of hint that even what we cannot see, that also exists, that is called dark matter. Not only that, we'll come to that point that this is not the only evidence of dark matter. I'll come to other examples of dark matter, but this basically gives us a jolt of our understanding of the subject, that even what we cannot see, that also exists. Not only that, that contributes to a huge amount of our energy budget of our universe compared to the visible matter source. I'll come to that point in a minute. But as I said, this profile you can find out, this feature you can find out in millions of spiral galaxies. So this is a generic feature. There is no other way out by which you can explain that. The only way you can explain this experiment is that along with visible matter, inside any spiral galaxy, there is huge amount of dark matter which you cannot see, but that must be there. So this is first kind of conclusion we get, first kind of surprise we get using our experimental data. Now I will come to that point once again. Now, as I said, our galaxy is just our Milky Way galaxy. Even if it looks a huge galaxy, it is just one galaxy among millions of galaxies. And this collection is called a galaxy cluster. So now, whatever you see, that is each point, each white point is a galaxy, and this is called galaxy cluster. So in each cluster, you have millions of spiral galaxies, and you can have other galaxies as well, like elliptical galaxy and all these things. So let's get some idea how big the size is. Okay, since physics is a quantitative subject, I'm talking about these things. So let's just try to have a feel of how big the size is. So this is just a cartoon. I have basically put two different galaxies. First is our galaxy Milky Way, and the second one is nearest galaxy, the closest galaxy you can have. The name is Andromeda. Amader Porshi galaxy, amader pasher badi galaxy. ঠিক আছে বাংলায় বোঝা গেছে আমাদের পাশের বাড়ির galaxy. So Milky Way, the nearest galaxy is Andromeda, and let's just try to estimate how far they are. What is the distance between them using our, say, class 5-6 kind of arithmetic, so to say. Okay, so simple calculation. We can experimentally find out that they are 2.5 million light years away. Our nearest galaxy is 2.5 million light years away from our galaxy. So let's just do this simple calculation. How much is the speed of light? Speed of light is this much kilometer per second, and 2.5 million light years. So you need to put it into seconds because the speed has been put in second. So kilometers per second. So 2.5 multiplied by million multiplied by 365 days into 24 hours into 60 minutes into 60 seconds. So if you do this thing, you can say how much kilometer apart they are. Okay, our nearest galaxy, how much kilometer apart is that from our Milky Way galaxy, and this is the result. Gono, kota shunno ache, duer gaye kota shunno ache gono. So it's a huge number. It's a huge number. And as I said, this is the nearest galaxy from our galaxy. And as I've already said, our own cluster, galaxy cluster, is made up of millions of these kinds of galaxies. So it's a huge size. Okay, but we can measure everything. We can measure everything accurately using our telescopes. And from there, let me come to this point about dark matter once again. That, yeah, so this is what you can do. Can you see the bottom part? I mean, is it visible or can you see the bottom part? I think, yeah.
So one bar is actually.
I think lower part
bar is actually coming.
Yeah, that's the problem. I cannot remove that one. That's the problem. Okay, so let's just keep it as it is. Okay, I'll explain. Okay. So okay. So what we do is that we basically. So we take all the galaxy cluster, we take one particular cluster and we take all the galaxies, the millions of galaxies inside that cluster, and we basically measure the velocity dispersion between each individual galaxy, so to say. The difference in velocity, each galaxy, and each one is moving, and each galaxy is not moving with a constant speed, the velocity is varying. So you're basically trying to measure the change, the difference in velocity. This is called velocity dispersion. And from there, using your virial theorem, you can basically estimate the mass, the total mass of the galaxy. So if you measure the total mass of the galaxy, there is independent way of measuring the total mass of the galaxy. So one is you measure the velocity dispersion, and from there you calculate, using your pen and paper, you calculate what should be the total mass of the galaxy. And then independently, using your telescope, you measure the total mass of the galaxy. Now that should match to each other. Okay, but unfortunately what happens is that this was given by Zwicky in 1933, way back, say 100 years back almost, that we get a huge mismatch once again. Just like in spiral galaxy, we get a huge mismatch of this thing. Okay, one we calculate from theory, and the other we basically directly measure from experiments, and that these two should match. This is what our understanding is, but they're not matching. There is a huge amount of mismatch. How much? 5 times, almost 80% difference is there. Okay, so what we say, we collect all the visible matter, we try to find out the total mass. Okay, so if the spiral galaxy, if the cluster is made up of visible matter only with the spiral galaxies, then the masses should match. But what we see is that there is a huge mismatch. They do not match with each other. So the only way you can explain that thing once again is that by considering, this is the Zwicky was the person who first proposed about dark matter. He said that inside the cluster, along with visible matter, along with all the spiral galaxies, there must be a huge amount of matter that we cannot see, and he gave the name dark matter for that. So just like as in the case of a particular spiral galaxy, inside the cluster we can have huge amount of mass. This contributes to 80% of the total mass of the cluster that we cannot see, but lots of experiments for the last 100 years or so, they are basically confirming the evidence of that. So we get the second hint of dark matter. The third hint I'll basically skip. This is called collision of clusters. So we are talking about one cluster. Now, our universe is made up of millions of clusters. First we talked about one galaxy, which is made up of millions of stars, including our sun. Then we talked about a cluster, which is made up of millions of galaxies. And now we are talking about our universe, which is made up of millions of clusters. And once again, sitting on this very, very small planet Earth, using our telescopes and using our brain, we can very, very accurately measure. We can find that out. We can very, very accurately measure that. Now, this bullet cluster is very interesting. This basically gives the collision between two clusters, merging between two clusters. And if that happens, from there we can also give a hint of dark matter, which I'm trying to skip. But what I will try to focus on is this, because this I'll come to this point in 10-15 minutes later on once again. So this is a new kind of telescope. This is called Sloan Digital Sky Survey Telescope. This is a project of NASA, American Space Agency. So this basically gives us a hint about the existence of dark matter at the largest scale in our universe as a whole. And I will come to this point later on. I'll explain, but all it says is that using Sloan Digital Sky Survey, you can get huge amount of data from outer space. And from there, you can say that not only in spiral galaxies, not only in galaxy clusters, but also in our universe as a whole. If you try to explain everything present our universe as a whole, you can explain that thing only and only way is that by assuming that in our universe, you must have 25% of dark matter. I'm not going to the details of this thing. All I want to stress upon is that I started with the word dark. And this is the point I'm trying to focus on. Using our telescope, the primary intention of the scientists was to find out the visible matter and see how the surprises in sciences come. Our intention was to find out the visible matter, but we found out something which is really, really unexpected. What we found out is that along with visible matter in our universe at every scale, starting from galaxies to galaxy clusters to our universe as a whole. Okay, I'll try to give you an estimate of the size of our universe, age of the universe, and all these things later on. But using everything, we find out at all scales, along with visible matter, we have a huge amount of matter that we cannot see, but that must be there. We get direct evidence or indirect evidence of that thing at all scales, and that is called dark matter. So this is the first surprise that we have. But let me just tell you before I move on to the next topic that till now we have not directly seen. As I said, they are indirect evidences. So there are lots of attempts to directly find that out. Why we cannot see them, I don't have the scope to explain that thing in this short period, but this must be there. This is what we have got. The hint is that this must be there in our universe at all scales. But the point that is left to do till now is that to find that thing out directly, as I said, just চোখে দেখা দরকার, সেটা আমরা এখন অবধি দেখিনি, because this is dark. So we're trying to find that out using our new telescopes, new tools, and all these things. And we do hope that at some point we'll be able to find that thing out directly. But the take-home message from here is that dark matter is some kind of thing that must be there in our universe along with visible matter at all scales. And if it is there, we must find that out. So this is the bottom line of this portion. Now I'll move on to the next topic that is called dark matter. As I said, I'm trying to focus on two different aspects, dark matter, and then I'll talk about the next aspect that I'm trying to explain that thing in a minute. I'm not going to name that one right now. So in my opinion, this is much more surprising than the surprises I was talking about till now. And that is why I have given it a name, that is dark art. This is much more surprising than the surprise we have been talking about till now. Now let me go back to the very early stage of observational cosmology, the guy called Hubble, on which the Hubble Space Telescope has been named. He was using the telescopes were not that developed at this time, because this is 1929, around 100 years back. But even using his telescopes, the experimental technique that was there during that time, he tried to directly measure something. What is that something? From our Milky Way galaxy, he just found out, see, each point over here is a new kind of galaxy. So what he tried to do is that he tried to measure, he just chose the nearby galaxies of our Milky Way galaxy, and he tried to find out two different aspects. One is the distance of the galaxy from us, and the other one is the velocity of the galaxy. As I have already told you, each galaxy is moving. No one is static. কেউ থেমে নেই, ঠিক আছে? প্রত্যেকে নড়াচড়া করছে. So what he tried to do is to measure the distance of the galaxy, each individual galaxy, from our own Milky Way galaxy, and the velocity of the galaxy. And collecting this information, he tried to plot that thing. So what he has done is, this is a very, very cartoon kind of picture, and this is a very age-old picture. I will come to the recent picture later on. So along x-axis, he put the distance of the galaxy from our own galaxy, and along y-axis, he put the velocity of the galaxy. And what he found out is this plot, that each point, see, you see black dot over there. Each black dot is a galaxy. Each black dot is a data point. So he just plotted that thing, and he tried to fit that thing. This is what we do in our laboratory. We get the data and we try to fit that data. The best fit curve we try to find out. The best fit curve, as he found out, is a straight line. And from the slope of that curve, we know how to find out the slope. dy dx is the slope. So from the slope of that curve, you can draw a very, very important conclusion. The conclusion he got even 100 years back is that the further the galaxy is, the greater is its velocity. Okay, প্রতিটা galaxy আমার থেকে যত দূরে আছে, তার velocity-টা, তার গতিবেগটা তত বেশি. And from here, a very simple pen and paper calculation can give you the conclusion. The second line is that the galaxies are basically moving away from each other. So this is a very, very important conclusion. Why? I will come in a minute. But the conclusion is that right now, that each galaxy, they are not moving away randomly. They are not moving away haphazardly. There is a pattern. The pattern is that each galaxy is moving away from each other with a particular kind of property. Okay, that property I'm going to explain in a minute. This property is this. So see, this is a cartoon, this is a balloon, and as if someone is basically bubbling the balloon. The balloon is increasing size, okay? And each point you get is a galaxy. So if you have a balloon and you have three different points, and তুমি যদি বেলুনটাকে হাওয়া দাও, okay? If you try to basically pump the balloon, okay? The balloon expands, and each point basically moves apart, moves away from each other. So you can see the points, you can see the galaxies, and you can find that they are basically moving away from each other. From there, what will be the conclusion? The conclusion will be that the balloon itself is expanding. Okay. Due to the expansion of the balloon, each point is basically moving away from each other. So this is the first conclusion he got. His conclusion was that since we see that each galaxy is moving away from each other, the conclusion is that the universe as a whole, on which each galaxy is located, that universe is not static. That universe is basically a balloon. That universe is basically expanding. And because of its expansion, each galaxy is basically moving away from each other. So this is a very, very, very important conclusion. And this is the first, so to say, first breakthrough of modern research in cosmology and astrophysics. Because it said, I mean, before that, the idea was that our universe is static. এটা একই রকম আছে, সব সময় থেমে আছে, একই রকম আছে. But this is for the first time back in 1929, this guy, Hubble, he proved that our universe is not static. Our universe is expanding. Our universe is growing in size, bigger and bigger with time. Why this is interesting, why this is basically surprising, I'll come later on. Okay, this is the point I'm going to highlight. But this is for the first time we found out that our universe is expanding. And nowadays what we do is that we make much more scientific methodology to prove that thing. What you do is that this is something you have learned from your, once again, 11 to 12 kind of knowledge, that is Doppler shift, the frequency shift, change in frequency because of movement of the object. So here, this cartoon, this guy is sitting on the Earth, and each point is basically a galaxy. We know using Doppler shift kind of knowledge, the frequency shift, that if it moves away from us, its frequency changes, frequency basically decreases, because of which wavelength increases. And if it comes to us, then the frequency increases, that is why wavelength decreases. So now, in the knowledge of cosmology, this is called red shift. So this is a different kind of frequency shift, but the property is similar to Doppler shift. So basically, it says, all it says is that if an astronomical object, say a galaxy, if it is moving towards us, we will see the wavelength to be decreasing. And if it is moving away from us, we will see the wavelength to be increasing. And from that, what we can do is this. We see the light. Okay, so using our telescope, we basically see the light. So light means basically we can catch the frequency and wavelength. So we see that further the object is, the wavelength is moving towards more and more red, because we know from optical, red has the wavelength of red light is the biggest. The wavelength of blue light is the smallest, the wavelength of red light is the biggest. Okay, so the further the galaxy is, its wavelength is getting more and more red. How can I prove that? I don't go into nobody goes to the galaxy. Okay, but we have our laboratory reference. From our laboratory, we know the wavelength of each light, right? Vibgyor, we know 3600 to 6400 angstrom. This is the range of wavelength of optical ray. So we know from our laboratory reference, we have that thing, and we compare the color with our laboratory reference, the color, the wave that is coming from outer space from a galaxy, and we see that we basically try to find out the difference in wavelength. So from this difference in wavelength or difference in frequency, we can actually find out how far the object is. Once again, just take a pause and try to think about the power of human intelligence. Sitting today, we can see the farthest object. I'll try to give you an estimate of how far that is. Farthest object right from our Mother Earth, using our brain and using our technology. So let me come to the point. So nowadays, what we do is that we just try to measure the change in frequency, and we give it a name that is called redshift. This is the modern technique by which we can do that. So if we do that, then cut to. Okay, I talked about 1929, and right now I'm talking about 1998. Okay. By the way, how much time do I have? Any feedback? Anybody? How much time do I have?
Continue, Supratik, that's no problem.
Okay, so okay, thank you very much. Okay, so once again, let me go back to the story of 1929. For the first time, this guy Hubble, he proved that our universe is expanding, and this proof goes beyond doubt. Everybody was convinced that our universe is expanding, and for the next 70 years or so, we were believing that our universe is expanding for sure. But I mean, you know, expansion is basically a velocity kind of thing. So you can try to find out the rate of change of velocity, that is called acceleration. Once again, from Newtonian mechanics, we know that thing. So we tried to measure the acceleration, the rate of change of velocity of our universe, so rate of change of size of our universe. And from our background theoretical knowledge based on, say, Newton's law of gravity, I mean, a modern version of that is called Einstein's theory of gravity, that is called general theory of relativity. I'm not going into details of that thing, but if you use your theoretical knowledge, you can show that even if, or you can prove that your universe is expanding, but from your theoretical knowledge, your prediction, your forecast was that the rate of change of size of our universe should decrease. This is what, I'm not going to the details of that thing, but from simple mathematical calculation, you can show that your universe should expand for sure. That is matching with experimental result, but your prediction is the rate of expansion should decrease. So in a bit technical knowledge, your universe should decelerate. Okay, this is so rate of change of size should basically slow down. Okay, that should decelerate. So this was our belief for the next 70 years or so, starting from 1929 till 1998, when this new project came, and that gave once again that came as a new breakthrough of modern science in astrophysics and cosmology, so to say. So technically this is called Supernova Cosmology Project. Okay, this is an American initiative of NASA, and and there are lots of different kinds of telescopes that are basically coming to this. I'll explain in a minute. This is one kind of telescope that is called Supernova Probe. Okay, this came in 1998. Let me just explain a little bit qualitatively what I mean to say. What is supernova? Supernova is basically death of a star. Okay, what do I mean by death of a star? Okay, so anything that is born, that must die. Why does a star die? A star dies because its internal fuel that is basically burnt out at some point. Okay, আমাদের সূর্য একসময় মরবে, বিকজ সূর্যকে আমরা দেখতে পাই, তার কারণে এর ভেতরে একটা কম্বাসন হচ্ছে, একটা ফুয়েল বেরিয়ে আসছে, এবং ফুয়েল যখন শেষ হয়ে যাবে সূর্য মরে যাবে। Okay, so this is the end of star, death of star, and death of star can have the death can have in different form. Okay, I'm not going into the details, but one name I should mention, because that you basically come across that name in popular science, that is called black hole. So one idea is that it may become black hole. There are 4 different kinds of ideas. The 4th idea is that it can have, at some point, it can explode. Okay, because a star, it has some internal gravitational pressure, and the combustion force that is going out, there is a competition between the two. At some point, when the pressure force dominates over the combustion force, it basically explodes. The stability is basically lost, and it explodes. This is called supernova explosion. Doom kore ekta bisphoron hoy. Supernova explosion. Okay, and sitting on our mother earth, once again, using our telescope, using our knowledge, using our intelligence level, we basically can find out hundreds of supernova explosion. So this project I was talking about, the Supernova Cosmology Project in 1998, for the first time they found out some conclusion using 48 supernovae, so to say. But right now we have around 1,000 or more supernova explosion data, and we are much more convinced about our conclusion. I'm coming to the conclusion, but all I want to stress upon is that the conclusion goes beyond doubt. Everybody is convinced. Okay, so what they did is 3 guys. Okay, supernova cosmology, there are 3 different guys: Rees, Perlmutter, and Smith. These 3 guys, at that point, what they did is that they found out 48 kind of supernova data. And once again, they tried to plot that thing. I'm not going to explain that plot. Along x-axis, they found out something which is called, I've talked about the redshift. Okay, along x-axis redshift, and along y-axis is called distance modulus. This is some kind of thing. I'm not going to details of this. So this is the plot, and this is not the plot they found out. This is a much more advanced plot using thousand supernova as we can get from now. But the pattern was found out for the first time in 1998 by these 3 guys. And what they found out is this plot. Okay, so each red point is a data point right now. Each red point is a supernova. Okay, this is called high redshift supernova type 1, a particular kind of supernova whose redshift is less than 1.5. Okay, so each data point is there, and once again they tried to draw a plot, the best fit curve. And the best fit curve they found out is this blue curve. Okay, so this is we need to keep in mind. Don't go into the technical details. The curve they found out is this blue thing. Now, using our theoretical knowledge, so this is the theoretical plot. We need to match, we need to explain the experimental results from theory. So what we get is that I don't have a pointer, so I cannot put that pointer in, but what I want to say is that everything else, like this red curve on the top or blue curve at the bottom or the black curve, each curve is drawn based on our theoretical understanding. And using each curve, we tried to match this experimental curve that is there in the left-hand side, the blue curve. And the only way by which we can fit the blue curve that we get from experiment is the middle one, the purple one. Okay, not the purple one. I mean, it's pretty close to purple one. Yeah, I think the green one. Yeah, the green one. Okay, so basically the intermediate one. All I want to say is that you can just compare these 2 plots and you can try to match. So the conclusion is very important. That is what I'm trying to focus on. So you get 48 supernovae and you plot that thing from experiment, and then using your theoretical knowledge based on Einstein's theory of general relativity, as I was talking about, Hubble's law and all these things, you try to match these two. Okay. And if you try to match that thing using your old knowledge that your universe should decelerate and all these things, you can have your matter content and you try to fit that in using your ordinary matter and dark matter, you cannot match that. The only way you can match that is this purple curve, and the explanation is this. The explanation is that, once again, please hold on. We said that universe is expanding, but for the next 70 years or so, we said that our perception, our understanding of physics was that the universe should expand, but it should decelerate. The rate of expansion should slow down. But this supernova data directly contradicts that. It says that no, for all these supernova data points, you can explain the plot only if you conclude that your universe is not decelerating. It is accelerating right now. See, this is really funny. You expected that the size of our universe should increase for sure. It should expand, but its rate of expansion should slow down. It should decelerate primarily because gravitational force is attractive. So each mass is basically attracting each other. Mass cannot be negative; they cannot repel. So gravitational force is attractive. So slowly and slowly, the rate of expansion should slow down. It should decelerate. But right now there is a big jolt. You get from experiment that your universe is not decelerating right now. Your universe is accelerating right now. At least today, your universe is accelerating. Now, how to explain that thing? Okay, your universe is accelerating. It looks like this. As if the lowermost bubble, this was the size of the universe at some earlier time. Then the next bubble, your universe, the size of your universe has grown, but the rate of change of expansion that has accelerated, and then the biggest one, it is further accelerating. So basically, the balloon I was talking about, the balloon is increasing, size of the balloon is increasing. Not only that, increasing at an accelerated rate. Lafiye badche size ta. Now, how to explain that? Because as we said, gravitational force is attractive. So this is in direct contradiction with your understanding of the subject. And the only way you can explain is this. The middle curve, not the topmost one, not the bottom one, the middle curve. The only way you can explain that thing is in simple language. Let me explain that thing. So there is this gravitational attractive force. Now, if you have someone which is much more stronger than this gravitational attractive force, and that is basically repelling each one. Okay? Gravity kache tanche, কেউ যদি থাকে যে দূরে ঠেলে দেওয়ার মতো শক্তি তার আছে এবং সেটা গ্র্যাভিটির যে শক্তি তার থেকে অনেক অনেক বেশি, তাহলে কি হবে? There will be a competition between the two, and the stronger one will win up. So this is a simple thing in our nature. So there must be something in our universe that gives you huge amount of anti-gravity, and at the end of the day, that wins over, that is much more stronger than gravitational force. So that wins over gravity, and because of that thing, even if gravity is attracting each one, our universe is expanding at an accelerated rate. And this is something, once again, that just like dark matter, we cannot see them directly, but that must be there. I'll come to the other experimental evidences in a minute, but that must be there, and the name was given is dark energy. Once again, this is a real surprise, and as I said, the history of science is always filled with different kinds of surprises. We always get something which we do not expect, and they are called breakthroughs. And these breakthroughs are the real challenges in science, because we need to explain that thing, we need to build up new models, we need to build up new theory to explain that thing, and those are the real challenges in doing science. And this is a cartoon. All of you know this guy. He is called Albert Einstein. This is the front page of the Science magazine, the world famous magazine. In 1998, the year supernova result was found out, and it said that this guy has lightened up some cigar, and this is the bubbles are coming out, and as if your universe is a bubble, and each bubble is getting bigger and bigger in size. And it says that the accelerating universe is a breakthrough of the year 1998. Okay, but 20 years down the line, today is 2020, more than 20 years down the line, we still see as a breakthrough. Why? I'm going to explain. Okay, is it okay? So I'll just take 10 more minutes. Is it all right? And then I'll finish. Shatoki, is it all right if I take 10 more minutes and I finish? Okay, fine.
Okay, that's fine.
Okay, fine. Am I getting too fast or is it too complicated? What do you think?
I think it's fine.
Okay, fine. Thank you very much. So the next 10 minutes, I'll try to convince you that supernova experiment is not the only one experiment, but we have lots of other experiments during the last 20 years that has convinced us beyond doubt that the dark energy must be there in our universe, and that must be much more dominant than the gravitational force. Okay, I'll come to that point. This is the latest survey. This is called Dark Energy Survey that has come into limelight in the last year, and this is giving us, I mean, I'm skipping some intermediate telescopes, so to say, because this is the latest one, and this has given us the first year data, and we are really excited because this gives highly precise and huge amount of data on supernovae. As I said, there are around 1,000 supernovae right now, so huge amount of data, and from the plot and all these things, we are much more convinced than these three guys, Rees, Perlmutter, and Smith, they were at 1998. And let me just tell you how convincing that is. In 2011, I think these three guys got the Nobel Prize because of this conclusion that they found out for the first time the evidence of dark energy. Okay, so darkest. Okay, so why darkest? Because in this point, I will try to focus on this aspect that from supernovae data, you get the first evidence of the next surprising thing. The first surprising thing was dark matter. The second surprising thing I'm talking about is called dark energy. Supernova data gave us first hint of dark energy, but now I will talk about other experiments because your universe is a huge one. You have different areas. I'll talk about them in a bit details. And from each experiment, you get the evidence of dark energy to the same extent. Okay, so that is what I'm trying to focus on, and that's I called darkest. This is much more darker than the darker one. Okay, one such experiment is called this telescope. This is once again a NASA telescope. This is called Wilkinson Microwave Anisotropy Probe. This is running for the last 17 years or so. Okay, it has given us the latest data, which is WMF9. And the next is called the Planck. This is European Space Agency telescope. I'm just giving you the names because in popular science you have or in newspapers sometimes you come across these names. These are artificial satellites. Each one is an artificial satellite, and each one is much more improved in technology from the previous one. So the Planck is the latest one. Planck gives us huge amount of data, and it has given us 3 different data in 2013, 2015, and 2018. I will come to that point in a minute. Okay, and this is an Indian initiative. We also have a plan of putting one artificial satellite, and this is in the proposal stage. We hope that this will come into limelight soon. This is a project we have proposed. Okay, so the next one, as I said, I talked about South Pole Telescope at the very beginning, and I said that I shown you this figure, which was not convincing. We can see nothing. We can see only ice and some points. Why this is just ice? Because as I said, this is an underground-based telescope. So this telescope has been dug inside 1 kilometer inside the South Pole. Okay, so if the entire telescope inside the South Pole, I've just zoomed in one point. I shown you this thing. Like one point I have zoomed in, and that looks like this because the rest of the thing, the most of the part is there inside 1 kilometer inside the South Pole. It has been dug in. That is why this is called underground telescope. Okay, so everything was there, everything is running, and this is giving us very precise data. Okay, why outside, why in space, or why underground? Because we try to reduce the noise created by the environment, created by us using mobiles and all these things, because we're using radio telescopes. So mobile data mobile signal that actually disturbs the signal. So we're trying to minimize the noise. Okay, so either we put it in outer space as a satellite, or we put it deep inside the South Pole where the probability of disturbance is minimized. Okay, so this is called South Pole Telescope. So you just see 1% of the total telescope. The rest of the thing is inside 1 kilometer inside the South Pole, inside the ice. Okay. From here, first conclusion from all these telescopes I was talking about. WMR Planck and South Pole Telescope. And there are all other telescopes as well. Like just last week, last week, there is Atacama Cosmology Telescope, a telescope running in Atacama Desert in Chile. That gave us huge amount of data we are excited about. So everything taken together, this is the conclusion, okay? That our universe started long back. Okay, this is the happy birthday to our universe. Our universe started from Big Bang. We have heard about that. Our universe started from Big Bang. 13.8 billion years back, our universe started. So our universe is that old, 13.8 billion years. It's much more older, okay? 13.8 billion years. Not only that, I'll try to focus on this. From here, once again, just take a pause and try to get surprised about the power of human intelligence. Okay, sitting today, we are looking into a sky. This is the sky. This is the first sky we can see. This is called cosmic microwave background. I'm not going into the details of the name. Sitting today, just using our telescopes and using our brain, we can draw the figure of the sky which was there 13.8 billion years back. 1380 কোটি বছর আগে আমাদের পৃথিবীটা কেমন দেখতে ছিল, আজকের দিনে আমরা শুধুমাত্র আলোকে টেলিস্কোপ দিয়ে ক্যাচ করে সেখান থেকে আমরা এই ছবিটা এঁকে দিতে পারি. And how convinced we are about the result, I'm coming in a minute. We are convinced about this. From here, don't go into the details of what is written over there. Let me just tell you. First conclusion, okay, so we can find out the temperature of the sky around that time, because we can prove from the data that our universe was a black body at that time. And from that black body, Planck's black body radiation, everybody knows about that. We know the black body spectrum. And from the black body spectrum, we know using Boltzmann law, you can find out the temperature. The temperature should be same, and using Boltzmann law, you can find out the temperature. And the temperature of our universe around that time is that is what is written over there, 2.725 Kelvin. So sitting today, we can find out the temperature of our universe 13.8 billion years back. So that is that temperature is extrapolated. The temperature is actually around 3000 Kelvin, but because of this time travel, okay, so the temperature we measure today is 2.75 Kelvin. But not only that, how precise the result is, we find that there is tiny temperature fluctuation. Why this is important, I'll explain. How tiny that is, this is like 10 nanokelvin to 200 microkelvin. We know about nano and micro, right? Micro is 10 power minus 6, nano is 10 power minus 9, okay? So there are tiny temperature fluctuations, and how precise the result is, once again, you need to be surprised that you just divide 200 microkelvin by 2.725 Kelvin, and what you get is 1 part in a million. 10 লক্ষ ভাগের 1 ভাগ যে ডিফারেন্স টেম্পারেচার ফ্লাকচুয়েশন, সেটা আজকের দিনে দাঁড়িয়ে আমরা 1380 কোটি বছর আগের যে ইউনিভার্স, তার 10 লক্ষ ভাগের 1 ভাগ টেম্পারেচার ফ্লাকচুয়েশনকে আমরা মেজার করে ফেলতে পারি অত্যন্ত অ্যাকিউরেটলি. And we have couple of different experiments going on, not only from one experiment, but each experiment gives the same result. So they are in tune. There is no contradiction between experiments. The experiment, the telescope I was talking about, each one says that you can get the result with that accuracy level. So we are convinced. Okay, and from there, let me not go into the details. From there, one can draw a plot which looks like this. Just look into the upper panel, the plot of the upper panel. Don't go into the details of that plot. Using that temperature fluctuation, change of temperature, you can draw this plot. And from this plot, you can see the first peak. That is a huge one. The first peak. Just look into the y-axis. That is something around 6,000 Kelvin, right? Okay, that is microkelvin square. That is written over there. The unit is microkelvin square. And from the y-axis, you can actually, from the height of the peak, you can conclude that once again, that our universe today that must have 70% of dark energy. I'm not going into the technical details. All I want to stress on is that. So the second surprise, from supernovae experiment, that was a completely different experiment. From supernovae experiment, using supernovae, we found out that our universe must have a huge amount. I did not talk about the amount. This is actually 70%. So 70% of dark energy must be there. That is actually responsible for the unexpected acceleration of our universe. And now we are talking about an experiment which is completely different, okay? That is probing the earliest possible universe. The systematics, the technology is different and all these things, and we are using a different telescope, different set of telescopes. And from there, our conclusion is the same, that our universe, along with visible matter and dark matter, we talked about them. We talked about visible matter and dark matter. Along with that, our universe must have 70% of dark energy. And what is the role of dark energy? As I said, the role of dark energy is to accelerate our universe unexpectedly, that is not possible from our ordinary matter or dark matter. So this is the second conclusion. I will skip some part and I will come to the conclusion in 3-4 minutes or so. So now, as I said, this is a cartoon once again. As I said, our universe started. Look into the left. Left is the beginning of our universe. Okay, don't go into the names and all these things. Our universe started at the very beginning, 13.8 billion years back. And if you go from left to right, this is how our universe has evolved. Started from a big bang, then after some time there are dark ages, nothing was visible. After that, the first stars were formed, and then galaxies and clusters, everything was formed. And in the rightmost corner, we are sitting today, and we are looking back in time. Okay, so we are sitting today somewhere in the rightmost corner, and from here we are basically looking back in time. So we can see everything, almost everything, barring the dark ages. These dark ages we cannot see. I'll talk about that later on. Okay, so you can see everything. So what happened is that our universe has evolved during this 13 billion years. Our universe has evolved, and you can see it today. Okay, আমাদের মহাবিশ্ব থেমে নেই, ঠিক আছে? এটা ইভলভ করছে, যেমন বাড়ছে তেমনি মহাবিশ্বে অনেক কিছু ঘটনা ঘটছে। হ্যাঁ, স্টার তৈরি হচ্ছে, গ্যালাক্সি তৈরি হচ্ছে, ক্লাস্টার হয়েছে। আমি শুরু করেছিলাম হাইড্রোজেন তৈরি হওয়া থেকে, তাই তো? সেখান থেকে বাকি সবকিছু তৈরি হয়েছে, এবং তৈরি হয়ে আজকের দিনে আমরা যদি পেছনের দিকে তাকাই, আমরা সবটা দেখতে পাই ইউজিং আওয়ার টেলিস্কোপস। ওকে, ফাইন। So I'll come in a minute. Okay, so this is I talked about these things to one digital sky survey, and using that we can find out the evolution of our universe that I was showing in the last slide. Okay, and from here what you can do, I'm not going into the details of this thing. Okay, from here what you can measure is something. Let me just tell you very briefly. What you can measure is that you can measure, so your universe at the very beginning, we have the temperature was used, the temperature was like 10 power 10 Kelvin, and photons and electrons and protons, all the ions, they were tightly coupled. They were in a stage which is called plasma stage. But as the universe expands, the temperature drops down, and protons and electrons, they come closer due to nuclear force, and they form hydrogen atom. This is what we know from our nuclear physics at this kind of knowledge. Now, when all these hydrogen atoms were formed, and then helium and all these things were formed, then photons, they basically came out of that, and those photons we are basically catching today. So what happens today is that, so we can catch those photons. Photon is there in cosmic background, and these hydrogens and all these things, loosely speaking, they are called baryons. They are basically oscillating in this background. So as if এটা একটা পর্দা, this is a screen, এবং সেই পর্দায় একটা ছবি আমরা দেখতে পাচ্ছি, একটা মুভি দেখতে পাচ্ছি। সেই মুভিটা কি না, পর্দাটা তৈরি হয়েছে ফোটন দিয়ে, এবং সেই জন্য আমরা দেখতে পাচ্ছি, ফোটন তো আলো, তাকে আমরা দেখতে পাচ্ছি। এবং তার উপরে যে ব্যারিয়ন গুলো, বাকি সমস্ত কিছু আমাদের ইউনিভার্সে যা কিছু গ্যালাক্সি ক্লাস্টার যা কিছু, তারা অসিলেট করছে। And this oscillation is something we can measure using that telescope, as I said, through one digital sky survey. We can measure it very accurately, and if we do that, from there we can draw this plot. I'm not going into the details. From there we can draw this plot, and this plot, you can compare this plot with the plot I shown, say, 2 minutes back. Okay, it looks the same. So this is a new experiment. This is probing a different area, but it gives you the same plot, and from here you basically draw the conclusion that once again our universe must have 70% of dark energy. And the last experiment I will talk about, and I'll finish in 2 minutes, is the Hubble Space Telescope I talked about. Okay, this is basically running for the last 25 years or so, and this helps us. So Hubble, as I talked about Hubble in 1929, he basically gave us data, some galaxies and all these things. He drew a plot. From there, he basically, for the first time, he said that our universe is expanding. But today, after 100 years or so, using Hubble Space Telescope, we get much more accurate result for that, and the result looks like this. So this is the plot we get right now. Same thing, what Hubble did. Along x-axis, you see distance written over there. Along x-axis, we draw distance. Along y-axis, we draw velocity, and we get a straight line. Okay, this is what Hubble got. But right now, we are much more convinced because the data points are much more precise, much more accurate, and much more huge in number. And from there, our conclusion is just same as Hubble, that our universe is still expanding. Just like Hubble said, our universe is expanding. From today's experiment, Hubble Space Telescope data, we get our universe is expanding. But the surprising point is that from here, you can also say that our universe is expanding, but not only it is expanding, but also this is accelerating. And from here, you can also conclude that our universe has 70% of dark energy. Okay, so what I said till now is that we do 4 different kinds of experiments. Okay, one is supernova experiment. Next one is cosmic microwave background experiment, third one is large scale structure experiment, and next one is Hubble Space Telescope data. So these are completely 4 different kinds of experiments. Each experiment has a number of telescopes involved, and all of them taken together give us the same conclusion that our universe today, along with ordinary matter and dark matter, we must have 70% of something which is called dark energy. Once again, why this is called dark? Because we have not yet seen them directly. Okay, the same thing, we have not yet seen them directly, but all these experiments conclusively prove that they are dark energy, and because of that, people have already got Nobel Prize. Okay, so this is a conclusion beyond doubt, and together, so this is a plot, together we get this result. I'm skipping this thing. So this is something I'll highlight upon. So this is called cosmic pie, left hand side. This is called cosmic pie, the round one, goal jeta dekhte paccho. It is sort of this is 100%. Amader universe ki diye toiri. And the color, non-blue color, what you see here, red and green and violet and all these things. This is visible matter. Everything is there. Neutral hydrogen, neutrino, stars, galaxies, helium, everything. So they just contribute to 4% of our universe. Just think about that. We can see lots of stars and galaxies and clusters in our universe using our naked eye, using our telescopes, all these things. But at the end of the day, your conclusion is really surprising. Whatever you can see directly, that contributes to only 4% of our universe. Only 4%. 96% is yet unknown. We know that that must be there beyond doubt from all these experiments, but we have not yet seen them directly. This is surprising. One is 25 or 26%, that is called dark matter. I talked about that. And the huge amount, the deep blue amount, okay, the navy blue amount, that is 70%, that is called dark energy. So dark matter and dark energy, the conclusion is that our universe that must be constituted of 25 or 26% of dark matter and around 70% of dark energy. But we are pretty sure, we are more than, much more confident that they must be there from all these experiments, but we have not yet directly seen them. And herein lies the real challenge for you guys who are the younger generation and who are basically aspiring to become astrophysicists or cosmologists in near future. So let me just summarize for them what we know and what we don't know. We know for sure that dark matter must be there, that contributes to 25%. Dark energy must be there, that contributes to 70%. But we have not yet seen them directly. আমরা এখনো খালি চোখে দেখি, মানে আমাদের যন্ত্র দিয়ে দেখিনি এখনো। তাদের এভিডেন্স গুলো পেয়েছি, তা থাকবে সেটা বুঝতে পেরেছি। There are other experiments as well. Other questions as well. We do not know what they are made up of and all these things. So this is a summary. I'm just trying to skip the rest of the thing. I will skip these things. I think the other speaker is there and I'm pretty excited to listen to him as well. So let me skip all this. But these are some of the experiments that are coming in near future that are trying to probe dark matter and dark energy directly along with other things. And in the next 10 years or so, most of them will start running. We'll try to get data, we'll get huge amount of data, and we expect that some of the surprises, at least, that will be resolved. And actually herein lies the real challenge of younger generation, that this is the high time you take up this subject. If you take up this subject as your research career, not only you'll face some challenges, but also you'll get satisfaction at the end of the day of knowing something that is yet unknown. And let me just conclude. This is the point over there. The point is not to pocket the truth, but to chase it. As I said, what is the purpose of doing science? The purpose of doing science is not just to help you brew your morning coffee, not just to make your day-to-day life easier. There is much more beyond that. That actually gives you a perspective of your position in the universe, that gives you an understanding of what is going on around you, and that at the end of the day gives you a revelation of what is going on over there and gives you much more pleasure. That is why we do science. Everything else, of course, they are much more important, but they automatically come, like the telescopes and experiments, the computer programming, all I said, that helps in technology development, that helps in computation development, and all these things. Okay, but they automatically come. At the end of the day, the target is to know what is unknown. And let me stop at this point and let me thank you very much for your patience. আমি আশা করি যে আমার ইংলিশ শুনে তোমাদের খুব অসুবিধা হয়নি, বা আমি খুব কমপ্লিকেটেড জিনিস বলেছি ফর শিওর, কিন্তু আমি যতটা সম্ভব সহজভাবে বলার চেষ্টা করেছি। তো আমার মনে হয় তোমরা সবটা বুঝেছো এটা এক্সপেক্টেড নয়, কিন্তু তোমরা কিছুটা আইডিয়া পেলেও এবং সেখান থেকে তোমাদের মধ্যে যদি দু একজনও মজাটা পাও ভবিষ্যতে এই সাবজেক্টকে তোমরা কেরিয়ার করতে চাও, আই উইল বি মোর দ্যান হ্যাপি এন্ড আই উইল থিঙ্ক দ্যাট মাই টক হ্যাজ বিন আ গ্রেট সাকসেস। সো নাও আই এম রেডি ফর কোয়েশ্চেন্স। যদি তোমাদের কিছু প্রশ্ন থাকে তোমরা যাতে ইচ্ছে বাংলা বা ইংরেজিতে বলতে পারো, আমি উত্তর দেওয়ার চেষ্টা করব। ওকে, সো
Thank you. Thank you so much, Dr. Pal. That was actually quite splendid and user-friendly talk, I should say. And at least, and also we got to know that basically we say that the future is dark. So you just showed us even the present is also very much dark.
Yeah, of course.
So that is the thing. So I'll just ask. There must be a lot of questions. I'll just ask Dr. Shorish Chakraborty to kindly go over the questions in the chat box and then ask that, read out to Dr. Pal.
Yeah. So thank you for a very good talk. So I will ask some of the questions that were posted in the chat box.
Yeah.
So the first one is from Raj Kumar. How did we get a picture of the Milky Way sitting inside the Milky Way?
Oh, that's a very very interesting question. Okay, thank you Raj Kumar for asking this question. আমি কি বাংলায় বলবো না ইংরেজিতে বলবো? ইংলিশে বলি, মানে বাকিটা যেহেতু ওরা বুঝেছে। ঠিক আছে, okay, sure. So it's like I'll give you a very 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 qualitative explanation, so to say, because the quantitative aspects is, I mean, for this I need to talk about lots of technical details and all these things. So it's just like I'm sitting over there. I'm a person. Suppose I am the Milky Way galaxy. Okay, so see, I stretch out my hand over there. Can I see my hand? Of course, I can see my hand. So even if my hand is a part of my body, okay, my eyes, using my eyes, I can see my hand, I can see my legs, I can see most of my body. I cannot see my eyes using my eyes. So it's just the same thing. As I said, our Milky Way is a huge one, and we are sitting in a very small corner of the Milky Way. So from there we can see the rest of the Milky Way, because this is a huge one. So just like we can see most of the part of my body, even if my eyes are a part of my body, I can see most of the part of my body using my eyes, because my eyes are really small compared to the size of my body. So it's the same thing. Our Mother Earth or our telescopes, its size is really small compared to the huge size of the Milky Way. Okay, so we can see the Milky Way even if we are located somewhere here. We can see the rest of the thing. This is a very qualitative explanation. I have a very quantitative or technical answer to this. I'm trying to skip that thing. Okay, I think this gives some sense to the question.
Okay, yeah. So the next question is from Binoy. So he asks whether there is any hope of detecting or seeing dark matter and dark energy in the future.
Of course, and that is why we do science. Okay, come on, people. At some point we were cavemen. আমরা গুহাতে বসে থাকতাম. Okay, from there, first of all using our curiosity, and secondly using our brain, we have come that long path. Okay, now we are that much technologically sound, and so everything is there. Okay, so we do hope that at some point we will be able to find them out. Okay, there are lots of experiments going on. I am not going to the details. I skipped the last of my talk, that is the probing the intermediate redshift. As I said, a new experiment is coming up, square kilometer array. I am also part of that experiment. This is a multinational project. 10-11 countries are, so India is also a part. I am also fortunately a part of that. That actually tries to probe the intermediate redshift region. Okay, I skipped that part, and we are pretty much hopeful that that will come into limelight in the next 5-6 years or so. We are pretty much hopeful that when the data will come, we'll be able to detect that. At least we will be able to get some hint. So for sure, I mean, sooner or later we'll be able to find them out, and that is the real fun over there. Okay, in science, the real fun is that what we have not found out till now, we'll be able to find that out in near or far future. Okay, of course, so we are very much hopeful.
So the next question is from Shayan and also from Binoy. So what is the state of matter of dark matter, and why can't we see it, and what is the potential candidate for dark matter?
Once again, this of course the answer is a huge one, so I'll just try to cut it out. Okay, First is we cannot see them. The simple answer is that because they don't emit light. We see an object only when it emits light. Okay, dark matter doesn't emit light, so we cannot see them. Okay, in little bit technical language, what does it mean? You know, there are interactions, right? So everybody is interacting with each other. Dark matter is highly non-interacting. If it does not interact with photon, okay, it does not disturb the path of the photon, it does not disturb the energy of the photon, it does not disturb the frequency of the photon. So we cannot see them, it must scatter. Okay, when we see something, the light goes there and it gets scattered. Now, if it does not interact, if it is highly non-interacting, then simply light passes through it. So we cannot see it directly. That's the simple reason. There are lots of candidates. There are standard model candidates. I mean, from particle physics point of view, there are beyond standard model candidates and all these things. There is a huge subject based on that. I'm trying to skip that part. But there are lots of candidates. The most acceptable candidate still now is called WIMP, weakly interacting massive particles. So this is the most acceptable candidate, but that is not the only one. We're trying to pin that down, even in, say, like CERN, even in particle accelerators. We're trying to build up mini universes. We're trying to build up a tabletop experiments where we will try to be able to find out dark matter at some point. We do hope that. Okay, so that is. So just to cut it out, that is the simple answer.
Okay. So the next question is from Shurojit. What dictates the shapes of different galaxies, like spiral and the things you mentioned? Yeah.
Okay, so internal structure and internal, so whatever is going on inside it, a galaxy is not empty, right? There are lots of dynamics inside that. I just skip that part. That is not possible to discuss over there. There is lots of dynamics going on. Depending on what kind of dynamics is going on inside a particular galaxy, either its size will be elliptical or spiral or spherical and all these things.
Sir, actually, is this depends upon the gravitational force?
Gravitational force is there everywhere. Okay, anything that has mass, you will have gravitational force. Okay, so it does not explicitly depend on gravitational force, but it depends on the dynamics that is going on over there. A spiral galaxy, dynamics of a spiral galaxy is different from dynamics of an elliptical galaxy. And there is something called HR diagram. Okay, you can put all the galaxies and stars on the HR diagram. So this is sort of galaxy classification you can do, loosely speaking. But the physical reason is this, that each type of galaxy, the underlying dynamics is different from each other. So that is why the shape of galaxy is different. Okay, like একটা থালা, আমি যদি থালাতে জল নিয়ে ঘোরাই তাহলে একরকম দেখতে হবে, আর আমি যদি একটা বেলুনের মধ্যে জল নিয়ে ঘোরাই দেখতে একরকম হবে। So it's just a manifestation of that. I think that.
So I'll move on to the next question. So there are some questions about the expansion of the universe you already answered. So one thing that is not answered is is the volume of the Earth, like should we expect the volume of the Earth to increase since dark energy is expanding everything? So
no. Because as I said, I tried to give you an impression of the total size of the universe. It's a huge one. And our Earth is nowhere there, almost nowhere there. Because as I said, our galaxy is just a data point in our universe. So our Earth, that is local gravity, dark matter or dark energy, if dark energy would have been felt in our Earth, then all of us would have been ripped apart. ওকে, আমরা দূরে চলে যেতাম, কিন্তু আমরা কাছাকাছি তো দেখি নিউটন লর জন্য কাছাকাছি সবাই আসছে, গ্র্যাভিটেশনাল ফোর্স কাজ করে একেবারে। সো দ্য সাইজ অফ দ্য আর্থ is so small compared to our universe. So for these local objects, dark matter and dark energy do not play much more role. So that is why this is called the astrophysical aspects. The cosmological aspects are the size should be much more large. The scales are much more larger than the size of a galaxy. Okay. I hope that explains.
Yeah, sure. So there is another question from Rajiv. So he wants you to explain the symmetries of galaxies and whether there is something called orientation of a galaxy.
I briefly answered to that already. Depending on structure and all these things, the galaxies can be classified into different categories. Once again, that is a much more technical thing I'm trying to skip. The galaxies can be, some of the galaxies can be classified as elliptical, some are spherical, some are spiral, and all these things. So this is called galaxy classification. Okay, so you can find that out, but that is a huge subject, so to say. Okay, but this classification has been done very, very accurately, and the conclusion is very convincing. Okay.
So I guess I'll ask the last question. There are some more questions coming up as we speak.
Yeah, but
just to stop, I'll ask the last question. So the picture you showed, where you showed the evolution of the universe, which was like a paraboloidal type shape picture, like from the Big Bang to the 13.8 billion years. That picture. So why is that particular shape? So this question was asked by Rajkumar.
Okay, once again, Rajkumar, thank you for this nice question. So the answer is, first of all, the answer is lies in this particular sentence that physics is an experimental subject, so we'll rely on experiments. So using all these telescopes, what we found out experimentally, very, very convincingly, I'm not going into the quantitative part, very, very convincingly is that, let me just elaborate that thing. Our universe started from a point that is called Big Bang. After that, for a very short while, just after Big Bang, for 10 power minus 34 to 10 power minus 32 seconds. It's a very short period, but that is something we can measure from here beyond doubt, very, very accurately. As I said, 1 part in a million we can measure. So just after Big Bang, for a very short while, universe has expanded by huge amount. Okay, so that's why this is called a super acceleration. This is called inflation. After which, once again, experimentally, we find out that universe has decelerated. Okay, one is called. So you will get to know about this. I have already checked that in your UG and PG course, the syllabus is there, and there I found out this radiation-dominated era and matter-dominated era. So at the very beginning, universe was really, really hot. Everything was relativistic, and at that time, radiation was dominating. Photon was dominating. So that time, the universe evolved. Universe size of the universe once again. That grew, but there was decelerating phase. Okay, so initially it was accelerating phase. After that, first decelerating phase was radiation-dominated era. After that, universe cooled down to a great extent. Okay, then everything became non-relativistic, as we know, and then matter-dominated era started. Okay, so there was deceleration. The third phase is deceleration, but at a different rate than the previous one. And right now, as I said, universe is once again accelerating due to dark energy. So it's a very fun evolution. This is what we get from experiment. First acceleration, then deceleration. Third phase is deceleration, but a different rate. And fourth phase is once again acceleration. So we are not going to. So this is what we get from experiment. From all these experiments taken together, this is what we get beyond doubt. And we are. So that is what I said. Our target is to explain that thing. To explain everything, we need to invoke these ideas like dark matter, dark energy, and other things are there. Skip those parts. So this is the state of the art.